All right, in this video, we're going to go through the last section of Chapter 4, which is on simple distributed loadings. And so, just to give you some perspective, again, we're at the end of Chapter 4. We started with Chapter 1. That was just, what is mechanics, and it talks about the different units of measurement, significant figures, some of the assumptions we make in rigid body mechanics, like the rigid body assumption, the particle assumption, concentrated force assumption, things like that. But okay, statics is, for the most part, the first course that you take dealing with mechanics. So remember, the subject of mechanics is you're studying forces on bodies and the effects those forces cause. Solid, liquid, or gas bodies. And most commonly, you'll start mechanics with solid bodies, in particular, rigid bodies. More specifically, rigid bodies that aren't moving or aren't accelerating. That's what we're doing in statics, here in statics. And so to start mechanics, the first thing we want to learn how to do, that we want to master, is vectors. Working with vectors in all kinds of different ways, specifically vectors that are represented as forces. So that's why we've spent so much time working with vectors, force vectors in particular, projecting them, adding them. Not just force vectors, even position vectors as well. Position vectors are a big part of mechanics, right? You have forces and positions of forces, things like that. There's all kinds of different ways that you need to learn how to work with vectors. Okay, and the reason is because what we're starting with is we have these rigid bodies, these solid rigid bodies that have all of these forces applied on them, these force vectors. We want to understand how to represent these force vectors, how to manipulate them, how to locate them on the body. But representing the load on a body is a little more complicated than just the forces and the force vectors. These forces can cause rotations. We have to represent this tendency of forces to cause rotations. So we had to go in depth on the concept of a moment, how to calculate a moment, what is a moment, how to project moments on a certain directions, different kinds of moments, moments about points, moments about axes, special kinds of moments, couple moments that come from two forces. So we learned how to represent vectorially the force system on any rigid body, including the rotations. And in the last couple of sections, we also learned how we can manipulate those force systems. We can simplify them, change their type without changing the equivalency of the whole system. We're just learning how to work with these force systems on these solid rigid bodies, how to work with them, how to represent them. And that's the idea. That's where we're starting in mechanics. We want to learn how we can represent these complex force systems in detail and manipulate and work with it. We want to understand how to do this without getting into the effect of those forces on the body yet. We haven't really gotten into that. Yeah, we did do that in Chapter 3. And if you're trying to tell the story of mechanics, the story of statics like a movie, then in my opinion, you would switch the order of Chapter 3 and Chapter 4. This would be Chapter 3, and then this would be Chapter 4. But they do it this way just because it's easier for the student to learn. I think that's why they do it this way. But as far as telling it as a story, you would put Chapter 3 after Chapter 4 here. All Chapter 3 is, if you think about Section 4.8, Chapter 3 is a special case of a force system where all of the lines of action of all of the forces meet at a point. It was that special case. But okay, again, before we move on to what is the effect of these forces on the rigid body, we want to make sure that we understand how to represent all of the different types of forces on bodies. And we're almost done fully understanding that. We've come very far, and we've almost looked at all the type of loading scenarios and how to represent it and how to work with it. But we have one more step. There's one more thing we have to talk about that we haven't talked about yet, and that's distributed loadings. Okay, I'm not going to go into too much depth on this here. We talk about this in depth in other videos. But remember, in the universe, there's only two types of loadings, at least that we're currently aware of in 2024. There's only two types of forces: body forces and surface forces, surface or contact forces. Body forces are like gravity, electricity, magnetism. They're these mysterious forces that we don't really understand how they work. Mysterious in the sense that, so if you throw something in the air or if you jump in the air, for some reason, the earth is pulling you towards it with no contact. And it's called a body force because the way we model body forces, the way we represent them, we think about it like, so if you throw something in the air, then every single atom in that object you threw has the same gravitational force acting in the same direction on it. The entire body has that same force vector. And so you can represent all of those forces with a single force acting at the center of mass of the body. That's why it's called a body force. If it's not a body force, then the force is going to be a surface force or a contact force. Again, that's the only two types of forces there are. So most of the forces that we interact with, we observe on Earth, are surface forces, right? To transmit these forces, there has to be some contact. There must be contact. Now, for all surface forces, that contact, there's going to be a contact area. There's going to be an area of contact of which the force is distributed. For every single surface force in the universe, every single one. There's no such thing as a point force, a force acting at a point. There's no such thing as that. You might say, well, wait a minute. We've been working problems in this entire course with these point forces, like shown here. Remember, we talked about this in chapter 1. One of the idealizations we use, so like we have the rigid body idealization. There's no such thing as an actual rigid body. Another idealization we use is the particle assumption. Another one we use is the concentrated force assumption. That assumption was that if the area of contact of the surface force, because there will always be an area of contact for a surface force, if that area of contact is small relative to the body you're analyzing, then you can model that force as just a concentrated force at a point and put the force at like the center of that area of contact. And that's completely fine. The accuracy of the final result, the inaccuracy that results from that assumption is completely negligible. And so up to this point in this course, every single force that we've dealt with has been a concentrated force assumption. Even the couple moments, it's coming from two concentrated force assumptions. But there are scenarios where the area of contact is not small relative to the entire body that's being analyzed. In that case, you can't put a point force. You have to put a distributed load, like shown here. Or if we look here, like shown here, for example, you have this crate, and if you're analyzing the forces on this structure here, well, the area of contact, that's the same length as this arm. So you're going to have to put a distributed load. Here they put a uniformly distributed load because the crate, it looks to be just the mass of the crate is uniformly distributed over the crate. So they would put a uniformly distributed load. This FR in the middle is, don't worry about that. Imagine this FR isn't there. The force you would put is this uniformly distributed load for the force of this crate on the arm. But if it was like a small piece, like a small heavy cylinder or something, then what we've been doing is that area of contact is small relative to the size of the structure, so you just put a concentrated force assumption there. So what this section is talking about is once you have a distributed load, how do you analyze it from there? But you as the engineer or the scientist, you're going to use your own judgment to apply the distributed load, to choose what load distribution to apply. For example, you'll look at this and you'll say you're analyzing this structure and you'll say, okay, based on this, the crates that are going to be on here, I'm going to put a uniformly distributed load to represent the force from this crate on the structure. That's the decision you make. But I just want to point out, you can go into more and more depth and more detail to get things, things get really detailed the closer you look at them. So like, even though if this crate had a perfectly distributed mass, like the mass of this crate was uniformly distributed over the entire crate, and it's acting, it's flush with the arm. I believe if you do like an accurate finite element analysis of the load distribution, it does something like this. It's like Like that's really what the load distribution is like. If you have a block of steel laying on the ground, and the mass is uniformly distributed, and it's perfectly flat at the bottom, and the ground is perfectly flat. It's not a uniform distribution. It's something like this. It's like right at the middle, the load is higher, and then towards the edges, the load is lower. But this should be perfectly fine, a uniform distribution. I mean, it depends on the accuracy you're looking for and how in depth you want to go. Just remember, quality engineering is about the assumptions you make and when to use assumptions to make things faster, more efficient, cost less money. So you don't just go into absolutely as much detail as possible. That's not good engineering. If you can make a uniform distribution assumption and that works fine for the problem you're trying to solve, then do it. That's good engineering. But again, I just want to point out that you're going to choose the load distribution to represent where the load is coming from. If the load in this crate was skewed to the right, then you might use a triangular distribution, right? Or maybe like a parabolic. So here's some examples. This looks like parabolic. Here's triangular. Triangular, it's sort of triangular here. It's got a rectangle at the bottom and then triangular at the top. These books here, they decided what they would do is get the entire weight of all of these books and then distribute that. And then because these books had a distinct difference, they're bigger, they did two separate distributed loads. They could have just said, let's take the weight of all the books and do one uniform distributed load. But they decided to do it this way. I mean, you could go, we're going to go, each and every book is going to have the weight of each book and have its own unique distributed load. I mean, but again, that you have to have a stopping point where you say that's unnecessary. That's going to take too much time for the problem I'm trying to solve. You have to think about it that way. Right? Here's like a piece of wood. I'm sure it has a load on it hanging off the edge of a structure here. It wouldn't be uniformly distributed. It would be kind of triangular like that, right? But again, you could do a FEA analysis, put load cells and stuff on a situation like this and get what the exact load distribution is, right? It would, I guess, maybe it's like hyperbolic or something, but depending on your problem, this should be fine. Maybe even a uniform distribution is fine. Here's some other loadings. Here's like I guess the load from the concrete. The deeper you get into the ground, there's more weight on top, and so they did this triangular load for the. I'm not sure how what they're doing here. That's more of structural or civil engineering. Here's a loading described from a sinusoid load distribution. Here's a load distribution for concrete. As there's more concrete on top, the pressure from the concrete is higher, and so they didn't do this they didn't do a triangular load. They did it parabolically for some reason. So okay, you've decided on the type of distributed load to apply based on the application. You've got your distributed load. You've put it on your body. What we're going to talk about in this section is how do you analyze that distributed load? How do you work with it? So let's take a look. Sometimes a body may be subjected to a loading that is distributed over its surface. For example, the pressure of the wind on the face of a sign, the pressure of water within a tank, or the weight of sand on the floor of a storage container. These are all distributed loadings. The pressure exerted at each point on the surface indicates the intensity of the loading. It is measured using pascals, so newtons per square meter, or pounds per square feet in U.S. customary. So a distributed load is a pressure, right? Force per unit area. That's how you specify the distributed load, as a pressure. It's some sort of pressure distribution over the area. So okay, let me show you the general case of a distributed load, which again, technically every load, every contact force that exists is a distributed load. Because here in this section, it talks about this is a simple distributed loading. We're going to see how in this section, we're just looking at a simplified case. In a later chapter, we're going to go into this in more general. But if we look here, when you're talking about a load over an area, what you're specifying is give two dimensions, right? Because an area is two dimensions. This is a flat area, but it doesn't have to be flat. You can have a curved surface, whatever, but you only need two dimensions to specify a point on any area, right? Areas are two-dimensional. So given two dimensions, so given a point on that area, what you get out is a pressure value. It's a pressure distribution. So like P as a function of X and Y, specify an X, specify a Y, and you get a pressure value. So you have the full pressure distribution over an area, the contact area. That's like the fundamentals of what a distributed load is. It's a pressure. Specify, give an input, give coordinates, so you input a point on that area and you get a pressure value. That's the fundamentals, as general as it gets of what a distributed load is, okay? It's a pressure, force per unit area. Now here in this section, we're going to go over a simplified case of a pressure distribution. So it says the most common type of distributed loading encountered in engineering practice can be represented along a single axis. For example, consider the beam or plate in figure 448A that has a constant width and is subjected to a pressure loading that varies only along the x-axis. All right, so they're talking about this here. The simplified case is that, so let's come back here. You could have a case where the pressure distribution, so the P, the output P, only varies in one direction, in the X or the Y direction or whatever, any direction. Like it doesn't have to be X and Y. You could have any kind of coordinate axes, but again, an area is two-dimensional, and you could have a special case where the pressure only varies in one dimension. With respect to the other dimension, the pressure doesn't change, right? If you come here in this is the X direction, the Y direction, the pressure doesn't change, right? Looking at this, that would be the case here as well, right? The pressure is not going to change in this direction, It's only going to potentially change in this direction. It doesn't because it's uniformly distributed, but let's say it wasn't uniformly distributed. It would still be constant here in this direction. So that's what they're talking about when they say it varies only along the x-axis. It's one-dimensional. Okay, this loading can be described by the function P. So P as just a function of X, newtons per square meter. That's the pressure distribution, right? It's only a function of X. Because at any X, once you get a pressure value, well then that's the pressure value at any point in the Y as well. You see? Okay, so now it contains only one variable X, and for this reason we can also represent it as a coplanar distributed load. To do this, we multiply the loading function by the width B of the beam so that this coplanar distributed load is equal to pressure distribution times B with units newtons per meter, figure 448B. Okay, so what you see here, you see this loading? Well, for planar problems like this, for these one-dimensional distributed loads, that's how the pressure is specified. You see? Here's the W, 60x squared newtons per meter, not newtons per square meter, right? Pounds per foot, not per square foot. Pounds per foot. This is for these 2D problems, this is how the distributed load is specified in a lot of cases in engineering. So what is this? What is this coplanar distributed load? Well, okay, if we look at this, the pressure distribution, newtons per square meter, since the pressure doesn't vary in the Y direction, you can multiply it by the thickness to simplify the load distribution. So here the thickness is constant B, it's B. But even if the thickness wasn't constant, even if the thickness was like, whatever, some function of X, the thickness was some function of X, the pressure distribution still doesn't change along the width direction. So if you had this B was a function of X, you would just multiply that function of X times P of X, and you would get a W of X. And what that would mean is that, what the Wx means is that at that x point, you've already multiplied the pressure by one dimension of the area because the pressure is constant in that direction. So now all you need to do to get the force over that area is just take a small dx, walk in the x direction, right? The idea is newtons per meter. If you're trying to find the load, the actual load, not the pressure, you multiply it by, well, like newtons per square meter, you multiply by the area. Well, for a planar problem, you can simplify that to where now the only thing you need to do is multiply it by a length to get the force. And that's what you're doing. If you had some irregular width as a function of x, multiply that times px, and at each point x, you know the one dimension of the area. It's already factored in. You just need to multiply that by some walk along the dx to get the force at that point, the planar force at that point. It's a force like here. If there's a force here or a force here, well, it's planar though. It's that same force into and out of the page across the dimension of the beam or whatever you're working with. Okay, so in engineering, a lot of times you're given, for these planar distributed loads, you're given W of x in newtons per meter. So you want to understand what that means. A lot of times the width B is constant, like for a beams, but even if it's not, you can still have a W of x. You just multiply the width as a function of x by the P of x and get the W of x. Using the methods of section 4.8, we can replace this coplanar parallel force system with a single equivalent resultant force Fr acting at a specific location on the beam. So that's what we want to do, right? We want to take a distributed load and reduce it to a simpler form that we can work with. It's hard to work with a distributed load when you're trying to do static analysis. But if we can reduce it to a single force at a point, if we can reduce it to a point force at a certain location, that would be much easier to work with. Reduce it meaning that the system is still statically equivalent. The distributed load and the point force are statically equivalent. So how can we reduce a distributed load to a point force at a point? Well, for reducing force systems, what we do is, let's say we want to reduce this to a resultant force in a couple moment at this point here. How do we do that? Well, the resultant force, let's do that first. We need to add up all of the forces, do a vector sum on all of the forces, and that's going to be the resultant force. Well, how do we add up something continuous like this? We integrate. So the resultant force, we need to integrate the forces. So how do we do that? Well, okay, let's start with this W of x. We know that W of x already has the width dimension factored in. All we need to multiply it by to get a force is a differential dx, right? And then we'll have the df. You see how that works? Even if b was a function of x, it'd be the same thing. Just take wx times dx and you get df, a differential force. This df is distributed across the entire width, uniformly distributed across the entire width. That's how you can think about it. It's the net force acting over that entire width at that point x. So that's df. We just need to integrate from L to 0 df. And that's what they do here. Integrating from across the length, wx dx. And then they call this they call this A. What do they mean by that? Well, wx dx, what is that? That's the area under the load distribution curve, at least the differential area, right? You take dx times the height, the wx, times the height of the curve. That's the area. And so when you do the integration, it's just this entire area. The area under the coplanar distributed load curve is equal to the resultant force, the simplified resultant force. Okay, awesome. So we have the FR, and we're going to put the FR at point O, right? We're going to put it here. We know how to get FR, we're going to put it here. We're trying to remove the distributed load and replace it with a resultant force in a couple at point O, like we've been doing. But next step is we want to calculate the couple moment. Well, we need to find the moment of all of these forces about point O. How do we do that? Well, we do another integration. Take the df, multiply it times x, right? That's the moment of df about point O, x times df, or the y-axis. There is no moment about the x or the p-axis. X times df. So integrate across the length x times wx dx, and you get the couple moment. But what we want to do is we want to get rid of that couple moment. We want to move the resultant force away from point O, the distance that matches that couple moment, so we can remove the couple moment. So that's what this x is. The x distance we need to move fr so that we can remove that couple moment. That's just, okay, so x fr is equal to that integral of x wx dx. And they put minus here because that's they're doing the correct sign convention. And you get this. The location of the resultant force, because now if we put the resultant force at this location, we can remove the distributed load for our static analysis. That location is this here, integral x dA. This is the area under the distributed load curve divided by the area under the distributed load curve. What this location is, it's the x location of the center of area, or the centroid under the distributed load curve, the wx curve. Now, in a later chapter, we're going to go into detail on how to find centroids of areas, center of gravity, but we just touch on it here in this section. Here's the centroid, or the center of area of this area underneath this curve here, this distributed load curve. That's the x location. Now, the centroid also has a y location, right? That's the centroid of this area has an x and a y location. But for this application that we're talking about here, the y location doesn't really matter. The y location doesn't matter. Just the resultant force is going to pass through that centroid and be acting on the beam where the contact is. They just put the centroid location here for illustration. They want to illustrate that this is the centroid location of this area. And we're just dealing with the x coordinate. That's how you find centroids. You divide the area and the kind of the moment of the area. Okay, so that's how you can replace a distributed load with a resultant force for the sake of static analysis. And again, we're going to go into more detail on how to find centroids and do the integrations in Chapter 9. But we're going to see that in many cases, the distributed loading diagram is the shape of like a common shape, a rectangle, triangle. And so we're going to use, there's tabulated results for the locations of centroids of these common shapes, and we might not have to do the integration every time. We can just reference those centroids. That's what they're trying to illustrate. They want to make sure that you understand that you're finding the centroid of an area. So you could go find tabulated results for centroids and use that to get the location of the resultant force, as opposed to having to integrate every time. Okay, so now let's work some problems.